The case of Ton 618. Ton 618 isn't just another entry on a cosmic leaderboard. It's the black hole that turned the idea of record-breaking into a paradox. Every time its name appears in scientific papers or headlines, it carries an almost mythical weight. 60 billion suns packed into a gravitational well so powerful that light itself stretches and fades trying to escape its glare. But what's fascinating isn't just how massive Ton 618 might be. It's how uncertain that number truly is, and what its very discovery reveals about the limits of cosmic measurement. The story starts in the late 196s, when astronomers were still puzzling over mysterious radio sources that didn't match any known stars. At an observatory in Bologna, radio surveys aimed at mapping the northern sky picked up an unusually strong signal. When cross-checked with optical plates from the Tonantzintla Observatory in Mexico, the same source appeared as a bright, blue-tinged point. It looked like a star at first, hence the ton in its name, but its spectrum held the giveaway clue. Deep ultraviolet emission lines shifted far toward the red end of the scale. That redshift meant it wasn't a nearby star at all, but a quasar, an active galactic nucleus powered by something extraordinary at its center. By the early 198s, astronomers were refining spectroscopy techniques to analyze these quasars in detail. When they looked at Ton 618 light, they found that its spectral lines were broadened almost beyond recognition. The gas racing through its accretion disk wasn't moving at mere thousands, but tens of thousands of kilometers per second. Feeding those velocities into dynamical models yielded an astonishing inference. The object driving this disk had a mass of roughly 40 to 60 billion suns. That single result catapulted Ton 618 from obscurity into superstardom. A glowing beacon declared the heavyweight champion of the cosmos. But those early calculations came with caveats. They assumed that the gas orbiting Ton 618 followed the same geometry as the accretion disks we see around closer quasars. In reality, no one could confirm that. A small difference in the disk's inclination could double or halve the estimated velocity spread, swinging the derived mass by tens of billions of solar masses. Adding to the uncertainty, the quasar's brightness depends on how efficiently matter converts to radiation as it falls inward. Change that efficiency factor, and the mass result changes again. Ton 618 became legendary not only for its supposed size, but for how fragile that estimation was. Zoom out to its cosmic address, and the picture becomes even stranger. The light we collect from Ton 618 began its journey more than 10 billion years ago, when the universe was less than a quarter of its current age. That means we're observing it as it looked during an era when galaxies were still assembling. Yet somehow, by that young cosmic age, Ton 618 black hole had already reached tens of billions of solar masses. Under standard models of black hole growth, even feeding continuously at the Eddington limit, there simply isn't enough time to reach that mass from any plausible seed. So either our physics is missing a shortcut, or our measurement is stretching the truth. Astronomers started exploring both possibilities. Some proposed direct collapse models, where enormous primordial gas clouds bypassed the normal star phase and imploded straight into black holes hundreds of thousands of times the sun's mass. Others suggested continual super-Eddington feeding, accretion rates so high that radiation pressure failed to blow surrounding gas away. Both ideas remain controversial, partly because they push against well-tested principles of radiation balance. But Ton 618 implied growth demands something extraordinary, so theorists keep those doors open. Meanwhile, observational astronomers have revisited Ton 618 again and again with upgraded instruments. Each time, they refine how they split its light, subtract background noise, and simulate the quasar's intricate structure. The revised numbers bounce between 40 and 66 billion solar masses. Some studies even lower it to about 35. That spread may sound drastic, but it highlights how much interpretation sits behind each figure. We can't weigh a black hole on a scale. We can only back out its mass from the curvature it imprints on surrounding matter and light. Despite the uncertainty, TON 618 retains a practical use. It shows the upper boundary of what our current models can reasonably support. If its true mass lies near the high end of estimates, then even the most optimistic growth theories strain to explain it. If it's lower, it still exemplifies how bright a quasar can burn when fueled by a powerhouse core. Either way, TON 618 pushes astrophysics to its conceptual limits. Let's step inside, at least in imagination. Its event horizon would stretch across about 200 billion kilometers, roughly 40 times the size of our entire solar system. A photon, traveling at light speed, would take weeks to cross its diameter. Around that horizon spins an accretion disk so energetic that it outshines entire clusters of galaxies. In visible light, it wouldn't appear black at all but blinding white-blue, with jets of plasma erupting along its poles and vanishing into intergalactic space. None of that light comes from inside the horizon. It's the collateral glow of matter losing its last fight against gravity. If you could somehow watch TON 618 up close, you'd witness optical illusions unlike anywhere else. The extreme curvature would warp background stars into rings and arcs, wrapping the universe around its silhouette. Time would crawl near its edge. To a distant observer, infalling matter would seem to freeze as it approached the horizon, but to the matter itself, the plunge would last only moments. Every physical concept, distance, duration, brightness, loses its ordinary meaning. That's why calling it the largest black hole almost misses the point. Its very existence distorts what scale means. In the scientific community, TON 618 has also become a case study in communication. The media love its superlatives because they sound definitive, the biggest black hole ever found. Yet astrophysicists who work on it emphasize that they're comparing models from inconsistent datasets. The uncertainties can reach a factor of 3, effectively erasing any clear ranking with rivals like PhoenixA or S50014 plus 81. In internal discussions, researchers treat those titans as belonging to the same ambiguous class, ultramassive black holes, rather than competitors. Beyond about 20 billion solar masses, every estimate sits on theoretical quicksand. Still, there's value in chasing the extremes. By pushing measurements to the edge, scientists expose the cracks in existing theory. TON 618 tells us that our understanding of black hole formation may be incomplete, that accretion physics might change under conditions we can't replicate nearby. Even if its exact mass someday proves smaller, the lesson remains that nature doesn't recognize our conceptual ceilings. There's also a psychological dimension to TON 618 fame. It acts as a mirror for our fascination with limits, the same impulse that drives mountaineers to tallest peaks or engineers to fastest speeds. Headlines about the biggest black hole satisfy a primal need for boundaries, but TON 618 paradox is that it erases them. The more we study it, the less sure we are of where those boundaries lie. It embodies the scientific truth that progress often begins where certainty ends. Recent attempts to re-evaluate its luminosity using improved distance calibrations have actually trimmed its reputed mass slightly, yet its mystique survives untouched. Whether 40 billion or 60, it remains a beacon from the universe's adolescence, screaming across cosmic history to remind us how young the cosmos was when such monsters already roamed. Through its light, we glimpse both the power of physics and the weakness of our metaphors. And so TON 618 endures not as a crown on a cosmic hierarchy, but as a question mark carved in light. It forces us to confront the gap between what we can deduce and what the universe really is. If a single object can appear to break growth limits, distort time, and challenge every definition of size, maybe the throne of largest black hole was never meant to be claimed at all. Because hidden closer to home, another contender waits, not blazing like a quasar but humming beneath the X-ray glow of a galaxy cluster. While Ton 618 shouts across time, this other giant whispers through heat and silence. It's called PhoenixA, and its quiet enormity may prove that the universe's true heavyweights don't always announce themselves with light. PhoenixA, the quieter monster. While Ton 618 dazzles across the universe like a cosmic lighthouse, PhoenixA hides in near silence. No flamboyant quasar glare, no blinding jets slicing through visible light, just a steady, massive presence deep inside the Phoenix cluster, roughly 7 billion light-years away. Here, in a realm crowded with thousands of galaxies and suffused with hot X-ray emitting gas, this hidden black hole exerts influence on a scale that makes even Ton 618 seem theatrical. It doesn't announce itself with brightness. It reveals itself through what it prevents, the cooling of an entire cluster's atmosphere. Astronomers discovered the Phoenix cluster in 2012 through NASA's Chandra X-ray Observatory, which detected a colossal concentration of superheated plasma radiating intensely in X-rays. Normally, that gas should cool, condense, and ignite vigorous star formation near the core. But something was rewiring the process. Streams of energy, jets invisible in optical light but bright in radio wavelengths, were blasting outward from the center, reheating the gas and throttling the cooling flow. The only phenomenon that could generate such power was a supermassive black hole devouring matter and converting gravitational energy into radiation. That central engine became known as PhoenixA. Estimating its mass, however, wasn't straightforward. Unlike Ton 618, whose quasar light could be analyzed spectroscopically, PhoenixA's black hole is shrouded by the very cluster it dominates. To weigh it, researchers turned to indirect modeling. They compared the X-ray luminosity of the cluster's central region to the rate at which gas appeared to cool. The idea is simple in principle. If the black hole supplies enough energy to counterbalance that cooling, the required output reveals how heavy it must be. When translated into numbers, those calculations yielded staggering possibilities, from about 12 billion up to perhaps 100 billion solar masses. Ever since, PhoenixA has floated near the upper theoretical limit of what nature might allow. This wild uncertainty stems from the method itself. The X-ray data tell us how brightly the gas shines, but converting that glow into mass depends on assumptions about efficiency, geometry, and the black hole's feeding pattern. Some models treat the outbursts as steady over millions of years. Others see them as short, violent flares. Each scenario changes the deduced energy budget, and therefore the mass. In some fits, PhoenixA eclipses Ton 618 by a comfortable margin. In others, it slips below it. The truth could lie anywhere between, and that range speaks volumes about what measurement really means. What makes PhoenixA fascinating isn't only its possible weight, but its temperament. Ton 618 is the showman of the cosmos, a quasar shouting its existence through cosmic dawn. PhoenixA is the strategist, regulating entire galactic ecosystems. By releasing energy into its surrounding cluster, it prevents the rapid formation of new stars that would otherwise fill the central galaxy with blue light. Instead, it maintains a fragile thermal balance across hundreds of thousands of light years. This feedback loop defines one of the great puzzles in astrophysics: how black holes, tiny relative to their host systems, can dictate the growth and evolution of entire clusters. To visualize PhoenixA's power, consider this. Each of its jet outbursts injects enough energy to equal the total luminosity of the Milky Way spread over hundreds of millions of years. That output isn't continuous. It pulses as accretion waxes and wanes. The result is a set of vast cavities, literal bubbles carved in the surrounding plasma, visible in both radio and X-ray images. Those cavities trace the history of the black hole's influence, expanding like shockwaves through the cluster. From them, researchers can infer how much work the jets have done against the environment, offering yet another indirect handle on the black hole's mass. When the numbers are summed, they again point toward an engine tens of billions of suns deep. What makes this case so revealing is the silence surrounding it. PhoenixA doesn't outshine everything around it. It shapes everything around it. In astrophysical terms, that difference represents two regimes of accretion. Ton 618 is radiatively efficient. Most of the matter falling in is converted into light. PhoenixA seems to operate in a mechanical or radio mode, ejecting energy mostly through jets rather than radiation. The irony is that the quieter mode may mask the heavier black hole. The stronger the jets, the less light escapes for distant telescopes to interpret, leaving us to reconstruct the monster by absence rather than presence. When scientists run cluster cooling simulations without such a powerful central object, the modeled galaxies form too many stars too quickly, contradicting observations. Insert a black hole of roughly 100 billion solar masses releasing episodic jets, and the numbers line up beautifully. It's a striking reminder that our sense of proportion in the universe depends on which kind of signal we notice. Sometimes the loudest entities are not the largest. Sometimes the giants speak in heat rather than light. The Phoenix cluster's environment also adds layers of complexity. Its intracluster medium teams with magnetic fields, turbulence, and merging substructures that all influence how energy moves outward from the core. Those interactions blur any clean distinction between the black hole's mass and its influence. A small adjustment to the assumed density of ambient gas can multiply or divide the inferred mass accordingly. Under such conditions, calling PhoenixA definitively the biggest borders on guesswork. Yet its existence proves something deeper, that black holes aren't isolated points but participants in cosmic ecosystems. Let's step back and compare styles. Ton 618 sits alone in deep time, a relic from the early universe where matter flowed freely and galaxies were primitive. PhoenixA lives in a mature cosmos, enwrapped by a massive cluster assembled over billions of years. The two embody different chapters of cosmic evolution, one displaying youthful hunger, the other long-term control. Judging which is larger misunderstands the point. They're incomparable precisely because they sculpt reality on different scales. Ton 618 across light years of individual brilliance, PhoenixA across megaparsecs of collective gravity. There's also an observational irony here. PhoenixA's host galaxy could house thousands of Milky Ways, yet to most telescopes it barely registers as distinctive. Its light is diluted by the cluster's glare. Without deep X-ray and radio surveys, we'd never suspect such a monster at its heart. That teaches an uncomfortable lesson. The brightest sources aren't always the most massive ones. For every blazing quasar we detect, there may be dozens of quiescent ultramassive black holes cloaked in cooler gas, their presence announced only through how they sculpt their surroundings. These quiet giants challenge our language. They don't conform to notions of object and size. Instead, they blur into their environments until the boundary between singularity and galaxy dissolves. Calling PhoenixA a black hole, singular, underplays that entanglement. It's more accurate to say it's a spacetime region coordinating the behavior of an entire cluster. That sounds poetic, but it's literal physics. Gravity couples everything within its domain so intimately that separating whole from host becomes artificial. And that brings us neatly back to the theme of this journey. If both Ton 618 and PhoenixA depend on vast chains of assumptions, if both exist to us only as reconstructions from distorted light and gas, then maybe the real story isn't which one wins the size contest. Maybe the mystery lies in how spacetime itself conspires to hide the truth from our measurements. PhoenixA reminds us that silence can be as deceptive as brilliance, that absence of evidence isn't evidence of smallness, and that reality at these scales mocks our craving for comparison. Because here's the twist. For all its quiet, PhoenixA may represent a fundamental limit in nature's design. Its theorized 100 billion solar mass threshold sits near the regime where a black hole's own radiation or jets disrupt further infall. If that limit holds, PhoenixA sits on the precipice of physical possibility. Beyond it, normal equations of accretion break down, hinting that the universe might impose self-regulating boundaries on growth. Just as biological systems stabilize after reaching maturity, cosmic structures might cap themselves through feedback, gravity and energy locking into equilibrium. But even that elegant balance collapses once relativity enters. Near such immense gravitational curvature, the very scales we rely on, distance, mass, luminosity, mutate with perspective. The farther we stand, the more they stretch. The closer we imagine, the more they compress. And so, whatever PhoenixA truly is, record breaker, boundary case, or something outside those categories entirely, it exposes the flaw in our reasoning. We keep treating black holes like contestants instead of conditions of the universe. If both of these titans are guesses drawn from shadows, then perhaps the real giant lurking behind them isn't a single black hole at all, but the physics that refuses to yield a simple measurement. And that realization sets the stage for the next step in our exploration. Because after uncovering how these monsters defy definition, the looming question becomes unavoidable. What happens to our notion of scale itself when space and time, the very fabric we measure with, begin to bend? The core problem: space, time, and scale. At this point, the puzzle stops being about measurement and starts being about meaning. Because underneath all the arguments over which black hole is heavier or wider hides a deeper contradiction.